Hey, welcome to your mini lesson for Chapter 10, Section 5, calculating the probability of independent and dependent events. So our first example is asking to find the probability of spinning a prime number on this spinner and flipping tails on this coin. So if we can calculate each of these probabilities separately, the fundamental counting principle says that we can multiply those probabilities together to get the probability of both of these events occurring at the same time. And so I'm going to first calculate the probability of spinning a prime number. And so here I go. Probability of prime equals. So remember, I'm going to do favorable outcomes on the top, total possible outcomes on the bottom. And my total possible outcomes on this spinner is 5. 5 possible numbers to spin. And spinning a prime number, now remember 1 seems like it would be a prime, but it is not, because we're talking about a number that can be divided by only 1 and itself, and since 1 is itself, it does not count. 2 is prime. Even though it's even, it's the only even prime number because it can only be divided evenly by 1 and itself. 3 is prime, and 5 is prime. And so the probability of spinning a prime number is 3 out of 5. Now our job is to calculate the probability of flipping tails on this coin. So we say probability of tails is, remember there are 2 possible outcomes, heads and tails, and so that's 2 on the bottom. There's only 1 favorable outcome of flipping tails, so the probability of flipping tails is 1/2. And so to calculate now the probability of both of these events occurring, I say the probability of a prime number and flipping tails is going to be probability of both of these things multiplied together. So the probability of spinning prime is 3/5, and the probability of flipping tails is 1/2. And so the probability of both of these events occurring, we're going to multiply these together. I'm going to go 3 times 1 on the top is 3, 5 times 2 in the denominator is 10, and there's my answer. I'm going to go back here. This was an example of independent events because the spinner and the coin didn't have anything to do with each other's outcomes. So now we have an example of dependent events, where 2 things are happening, and the outcome of one is going to depend on the other. So we are at a game show, and we have an audience of 100 people. Pretend you are there. You're with 5 of your relatives and 6 of your friends. At the game show, they're going to randomly draw people out of the audience, and your job is to figure out what is the probability that one of your relatives is going to be chosen and then one of your friends is going to be chosen. So I'll erase that so we can get a clearer picture of what's happening here. So as we did before, we're still going to figure out what the probability of these 2 events happening independently of each other are. So first I'm going to calculate what is the probability of one of my relatives being chosen. So say probability of relative is going to be, well, remember our total possible outcomes is 100 people in the audience, and there are 5 of my relatives, so the probability of that happening is 5 out of 100. Then they're asking, what is the probability of one of your friends being chosen? So I'm going to calculate that. Probability of my friend. Now, assuming somebody's already been chosen out of the audience, there's no longer 100 people in the audience. Now there's 99 people. So our possible outcomes have changed, and that's why these are dependent events. I still, assuming one of my relatives was chosen, that means 6 of my friends are still left to choose from. And so the probability of choosing a friend out of the audience is 6 friends out of now 99 possible people to choose from. And so the probability of both of these things occurring, that is the relative being chosen, that says relative, fix that. The relative being chosen, and then a friend being chosen is going to be 5 out of 100, that's the probability of my relative, multiplied by 6 out of 99. Remember, that's the probability of my friends being chosen. And I think the easiest thing to do here is to simplify these fractions first. Simplify 5/100ths, because I can divide both of these things by 5. So if I do 5 divided by 5 is 1, 100 divided by 5 is 20, and so I'm going to turn that into 1/20th times, and I'm going to do the same thing with this 6 over 99. I know I can divide both of these by 3, so if I do 6 divided by 3, that's 2. 99 divided by 3 is 33, and so that fraction turns into 2 over 33. And let's see if I can extend my page here. There we go. Now I need to multiply these, so let me get a different color, get blue. I can do 1 times 2 across the numerators, or 20 times 30 and 20 times 33 in the denominator, but I see an opportunity here with this 20 and this 2 that I can simplify before I multiply. So I'm going to go 2 divided by 2 is 1, 20 divided by 2 is 10, and now I'm going to multiply straight across. So I'm going to go 1 times 1 on the numerators, and 10 times 33 in the denominators. It's 1 out of 330. That's the probability of choosing a relative and then a friend. Last example. This is good test-taking strategy here. So imagine we've got these 3 questions, all of which have 1, 2, 3, 4, 5 choices. And if we were to randomly guess the answer for each of these questions, what is the probability of answering all 3 of them correctly? And so there's only one correct answer here. So there's 1 favorable outcome out of 5 choices. There's 1 correct answer here. 1 favorable outcome out of 5 choices. And also, in the last question, 1 correct answer out of 5. And so the probability of all of these things happening would be to multiply all of the probabilities together. So this is the probability of our correct answer for the first one times the probability of our correct answer for the second one times the probability of the correct answer for the third one. It's going to give us the probability of all 3 of these things happening in a row. So if I multiply my numerators, 1 times 1 times 1 is 1. And if I multiply my denominators, 5 times 5 is 25. 25 times 5, excuse me, it's 125.